This is our project for ETME 2100. I'm William Whitney.
And I'm Ervin.
We created a distance monitoring system. Tate is going to give us a system overview.
So as you can see here, the system is made up of two major components. You have the sender and the receiver. The sender has the ESP32-S3 feather paired with a VL53L1X time of flight sensor. Its job is to take distance measurements, convert them into feet and inches, and transmit them over Bluetooth low energy. The receiver is another ESP32-S3, but this one has a reverse mounted TFT display. It acts as the BLE central device. It scans, connects to the sender, receives the distance data, and displays it in real time. Both boards run on LiPo batteries, both have battery telemetry, and both have low power.
Okay, let's get started off by going over a system overview. The system is made up of two major components, the sender, right here, and the receiver. The sender has a ESP32-S3 paired with a VL53L1X time of flight sensor right here. Its job is to take the measurements, convert them into feet and inches, and transmit them over Bluetooth low energy, also known as BLE. The receiver is another ESP32-S3, but this one has a reverse mounted TFT display right here. It acts as BLE's central device. It scans, connects to the sender, receives the distance data, and then displays it in real time. So as you can see here, this is the ESP32-S3, and this is what they call the TFT reverse display. Both of these are powered by 1200 milliamp LiPo batteries.
Now, for how the VL53L1X time of flight sensor works. It is not a traditional ultrasonic sensor or infrared proximity sensor. It's a true time of flight sensor, which means it measures how long it takes for a burst of 940 nanometer infrared light to leave the sensor, hit a surface, and return to the detector. The detector is built out of a SPAD array, single photon avalanche diodes, which can detect packets of light at extremely small time scales. Because of the measurement is based on time, not intensity, it's much more accurate and less sensitive to color or texture. In the setup, we run it in long range mode with a 20 millisecond timing budget, which gives us up to 50 measurements per second. The sensor returns distance in millimeters, and the microcontroller converts that into feet and inches before broadcasting it.
Now let's talk about the battery monitoring system. Both the sender and receiver have battery monitors. The ESP32-S3 feather comes with built-in voltage divider that lets the ADC measure the LiPo battery. The voltage is read by the microcontroller, mapped to a percentage, and then transferred from the sender to the receiver along with the distance data. On the receiver side, I've added that to display that. It shows a status bar of the battery depending on the battery health. Higher than 4.5 volts shows good charged battery. Anything above 2.1 volts shows medium health battery. Anything under 2 volts shows low health battery. Now, let's talk about power management and sleep mode. To make the system suitable for real-world portable use, I implemented a low-power sleep mode. When the BLE connection drops, meaning the receiver's out of range or turned off, the sender automatically stops ranging, turns off the NeoPixel, and enters a low-power IO mode. The receiver also shuts down the display to reduce consumption until new connection is detected. This significantly extends the battery life that I was speaking of earlier, especially when devices are not actively being used. The range is about 10 feet. Anything outside of 10 feet, the receiver will disconnect.
BLE, or Bluetooth Low Energy, is what connects the sender and receiver. The sender advertises a standard Nordic UART service. which basically turns BLE into a low-power serial link. The receiver scans for that advertisement, automatically connects, and starts reading incoming packets. In this project, I optimized the connection interval to be about 12.5 milliseconds. This significantly reduces the latency and increases the effective update rate. Using BLE over Wi-Fi gives me lower power consumption, faster connection, instant pairing, and enough bandwidth for sensor telemetry. This allows us to have real-time, smooth data screening. Now let's talk about the performance of these objects. Right now, this is still in a development state, as it could be optimized a lot further. With BLE transmission, you can only send roughly 10 kilobytes of data per second, meaning that the transmission rate can be slow and can be laggy. As you can see, at the beginning of our transmission rate, it's pretty good, 3 inches, and as I move this back, the reading will increase with me. However, if you were to let this run at more than probably an hour, the readings begin to build up and display inaccurate material data. This is due to a slew of factors. The ESP TFT reverse has a build log of this data and struggles to display it all at one time, so it has to sort and parse through the data to figure out what to display at the correct time. Like I said, this is a buildup that happens in a log. And then for the sender can actually end up sending too much data at one time, overwhelming the TFT. However, the sender can also itself be optimized with the TOF sensor. The TOF sensor sends data at an extremely fast rate compared to the 2 ESPs that are powering it that can handle. This ESP specifically only has 2 megabytes of RAM, so it can only take this data at a certain limit, and then it's overwhelmed and starts to bog and throttle neck. The TFT reverse, like I said, is the main culprit of the bottlenecking, as it has to read the data and then display the data at a relatively quick rate, which it is slow to do. So overall, I would optimize these to be a better the best way that I could see in optimizing these two devices to complete this project would, instead of using BLE Bluetooth transmission, I should use Wi-Fi or ESP now Wi-Fi transmission. With this, you can send up to 50 kilobytes per second at a much quicker rate. Sometimes with the right hardware and components, you can send up to 500 kilobytes per second. With this though, I am really limited to a max of 10 to 20 kilobytes per second, depending on if I'm running BLE or just regular high Bluetooth. So this is the overall project for the measurement system, and this is the current optimizations that I would do. Now that you've gotten to see the sender and the receiver, I would just like to say thank you for watching our project and watching our video. A lot of work and time went into creating the sender and receiver, especially in CAD, coming up with the code. Me and Tate split a very long time on these things. We learned a lot going through this. We really loved the idea of the IoT devices. This is a very good indication of Industry 4.0, and it's a great way to learn about Industry 4.0 and automation, and how it's essential that we should learn how these devices can talk to one another on a low level, meaning that it would be hard for people to intercept these signals and tamper with them, especially for cybersecurity reasons and stuff like that. I also want to give a special thank you to Dr. Verrol. He has been an amazing teacher throughout this semester and throughout my collegiate career. So I just want to give a thank you to everybody involved in making this project happen.